Hey, exponential growth and decay. It's 4, 5. Now, this is one that's used a lot for predictions. All right, and it's actually kind of ironic that we're teaching this in the middle of a pandemic. All right, because a lot of times those are the ones that it's used for. All right, it's used for spread, looking for population growth, those types of things. All right, but in a case like now, I mean, you remember the graph at the beginning. All right, so back in April when we shut down, we had, it was kind of going like this, right? And then what happened recently? All right, that right there is exactly an exponential growth model. Okay, think about it. So a linear growth is going to grow at a steady pace, right? It might start with you and go to him and go to her. So we went from 1 to 2 to 3 to 4. All right. Exponential growth says, all right, so maybe you have coronavirus and you breathe. So me and you are now sick. Okay. So then the next day, we have 3 infected people. Guess what? You're all sick now. But that's how stuff spreads, okay? If you look into this stuff with the whole breeding of people, whether you believe it or don't believe it, it's fine. All right, we're not getting into that debate. But one person could spread it to 2. Those 2, each of them spread it to 2. All right, so now we have 4 or 6. You know what I mean? And every time it just doubles and doubles or triples or something like that. Okay, that's exponential growth. All right, so exponential growth, this is used a lot in predictions, and we'll go say prediction models. Okay, like I said, this is ironic during the pandemic. All right, you guys want to talk about stuff you see in the real world, buddy? You're living in it. All right. All right, so I guess I wish it wasn't a reality, but hey. All right. It was back in like the 20s. That was it's the Spanish flu. It lasted for like 5 or 6 years. Yeah. So that happened. The Spanish flu happened whenever all our soldiers came home from World War One. What's that?
So this could last till my end of my college.
It's gonna last for a while. Agreed. I mean, if the vaccine comes out and the vaccine works fine, probably another 6, 8 months, then it'll be under control. And chances are this is going to be like the flu. Like the flu happens every year, right? There's people who always get flu shots, but there's always a flu season. Probably for at least the next 20 years of our life, there's going to be a corona season or COVID season. You know what I mean? Until it gets completely gone or out of our system.
Morgan was saying that in 2018, a lot of there was more people that died from the flu than have due to COVID. She said something about how.
All right, we're not getting into the debate on that one. You can save that for later. All right, so exponential growth and decay models. These are the formulas for it. So we have f of t equals a sub 0 of e to the kt, or we also have a equals a sub 0 e to the kt. All right, so you look at it 2 different ways. Okay, so with this then. I don't want that. There we go. All right. So here's the big thing then. If k is greater than 0, then it equals growth. And if k is less than 0, it equals decay. All right. So if we look at our exponent up here, if this is a positive number, that means we're increasing. Okay. If it's a negative number, that means we're decreasing. All right, and then a couple things about it, that a sub 0 is your original amount, and that's at time 0, t equals time. Okay? Your A, or your big A on the left, is going to be your amount at time t. And K is your constant representing your growth or decay. All right, so we're going to do an example. So we're going to go with the U.S. population. All right. So in 1970, there were 203.3 million people in the United States. In 2010, there were 308.7 million people. So here's our question then. We want to find an exponential growth model. All right, anytime it says find the growth model, all that's saying is give me an equation. Okay, that's all that means. And then 2, we want to find out when will the population hit 335 million. Okay, so that's the 2 things we want to do. Now, as we're talking about modeling, I had a class in college. It's called math modeling. Seriously, it was my favorite math class I took the whole way through, really through my entire career. And what it was this type of stuff. It was making predictions, making equations that represent situations. But the one thing that was kind of cool, so what he would do, we were talking like calc level math, of course, but he would give you a whole bunch of, you had these projects. You didn't have tests or anything like that. You had projects. So he'd give you a whole bunch of math that was kind of related, but there was no units, there was no description of it. All right, so you might have 1970 is 203.3 million. This he wouldn't give you U.S. population, so he would give you a whole bunch of stuff that was connected. You had to come up with a story to go with it, right? So that was what the modeling thing was. So there was a whole bunch of work. It was a big series. Yeah, it was a big series of stuff. But our final project, he gave us this whole thing. We did it on a like an arms race. You know what an arms race is? So, for instance, an arms race would be, so like if us and Russia, we're comparing how much military strength we need. Okay? If they have 2 nuclear missiles, how many tanks and men do we have to make it back to even? You know what I mean? Like, what is that? So you like assign values to, like a tank is worth 25 soldiers, just that kind of stuff. All right, it's called an arms race. So you want to make sure that you're either ahead or equal. We turned this arms race thing, and we did this whole thing. We kind of like BS'd, and we made it kind of comical at times in there. Like we had stuff like "Take that, Mr. Putin," and we put phrases like that in there whenever you increase. This thing came, and we had to write in this math language. It was like this special program. It's called LaTeX, where you could type your paragraph, and then you had to code in the stuff. So whenever you coded it in, it came out really nice and neat. It was professional math writing. We turned it in. It was 49 pages long. 49 pages long. And me and my buddy Chad, that we worked on it together, we like after this thing came out, because like you type it in Notepad, so you had no idea how long this thing was. It was just a whole big series of coding essentially. So then you hit convert. It converted. It was 49 pages. Oh my God. Like we knew it was good. But we printed it out, and you can email it to him or just drop it in his mailbox. Oh, we printed it out, and we walked up, and we knocked on his door. We're like, "Hey, Dr. Bukowski, check this thing out." Like threw it down on his desk. He's like, "What are you doing? Bring me a book?" So he kept it and like he has it saved somewhere. Um, but it was. All right. Yeah, until you make one mistake.
Yeah, and then you go back there and you're trying to figure out what you did wrong for about 4 hours.
All right. So let's look at this guy. So we want to find a growth model for this, and then we want to find out the population. We're going to use it to make a prediction. All right. So we have to start with our A equals A of A sub 0 e to the kt. Okay? And we're going to say here that T is years after 1970. So say it's years after 1970. So in this case, our initial value is the 203.3. All right? And that would be at time 0. Does that make sense? We want to make something in reference to time 0. All right, so let's plug some stuff in here. So my initial value is 203.3. All right. So that's e to the kt. So I don't have any of the rest of this stuff. What I do have to find though is what's that?
That's the starting point.
Yeah, a sub 0 in our notes. A sub 0 is our starting value. Think of it like your y-intercept. Okay. Now, here's the problem. We are going to leave this t in here. Okay, that's our x. All right, that's the value that we want to be able to put in anyway. We have to find this. We have to find this constant. Okay, so we have to solve for k. So let's take in everything we know. We know that in 2010, what's our population in 2010? Good, 08.7. And that's equal to the 203.3 e to the kt, right? Now, I actually do know what my t would be here. Because in 2010, how many years have passed? What's my time? 40 years. Okay, so I know what my t is. Okay? So now we want to solve for k. So let's start off, just get this e thing by itself. So let's divide both sides by 203.3. All right, we divide by 203.3. We're going to get, I'm just going to leave it as that for now. So I've written on my notes, so we'll just go with that. And that's equal to e to the 40k, right? Now, I want to get rid of this exponent for this e somehow to get the k down, right? Now, we've been doing this the last couple of days. Can I apply the natural log to both sides? Yeah, let's apply the natural log to both sides. All right, so I apply the natural log to both sides. And then that's going to leave me with all this over natural log of 308.7 over 203.3 equals, that's going to be 0.417. So 0.418. Okay? And that's equal then to 40k, right? You with me on that? Just apply the natural log to both sides. Now, I want to get k by itself. Divide both sides by 40. All right, divide by 40. I'm looking at 0.01. And anytime you do this, guys, your number's going to be really, really tiny. It's going to be, okay? Very rarely are you going to get something over 1. All right, a lot of times it's going to be point something or negative point something like this. All right, so that's my k. So now, to plug it back in, my model for this one, oh, I already have most of it here. A equals 203.3 e Now I know my K, or my constant of growth or decay. In this case, it's growth because it's over 1. It'll be 0.01 t. All right, so there is my model for this. Okay, that equation right there will give me any value I want. It'll give me the population in any year, and so on and so forth. Now, if I wanted to find the population in the year 1990 using this model, well, then I could just plug a 20 in for t. It's 20 years after 70, right? So that's the easy one. If you plug in time, no problem. It's going to give you the population. We're asking for, though, when will the population hit 335 million? So we want to know when this number is going to be 335, right? So plug that guy in. So we want 335 to equal 203.3 e to the 0.01 t. Okay, so there's two different options. One, you can figure out when it'll hit that population, or two, what the population is in a certain year. So we went with the first one. All right, so we just set that equal. Well, now we can go ahead and kind of solve it like we did before. Divide both sides by 203.3. All right, and then apply natural log, right? So I do that. Natural log of 335 over 203.3 is equal to, natural logs applies to 0.01 t, and then divide the whole thing by 0.01. I'm just going to put it all on my calculator at once. So you get, I think it's like 49.892 or something like that. But that doesn't make much sense, right? We'll just call it 50. And again, all I did was plug that in my calculator. Okay. So we got an answer of 50. Well, we were looking for a year, weren't we? So 50 doesn't seem like a reasonable answer. But if we think back, T is our years after 1970. So what year were we going to hit 335 million? $1970 plus 50 is going to be 2020.
I don't know about that.
Oh, I didn't hear you.
The year we shall not name.
A year from hell. That's right.
It's gonna be like the Star Wars.
There might be people who locked down for a while. Well, that was, I mean, you guys know what caused the first baby boom, right?
World War II.
Yeah, when everybody came home, hadn't seen people for a couple years.
Say that now.
Okay, any questions on?
Okay.
Hey, okay. Wonderful problem. Let's do one more. Let's do one more here. Okay. So another thing that you're gonna find is talking about things called half-life. Another big thing is radiocarbon decay. You guys know what that is?
No.
You guys know what radiocarbon dating is?
It's so familiar, but I don't.
Okay, radiocarbon dating. I'll pause this for a second. Radiocarbon dating is what they use to say, like, this bone is 14 million years old from a dinosaur, those types of things. All right, so what it does, they take this thing is called carbon-14, it's a mineral, and they know how long this lasts, so they measure how much of it has survived, so they can use that to backtrack and figure out how old it is. I don't agree with it, so that's why I took the earpiece off. It's kind of one of those, I don't get into it, it's a religion versus science type thing. That's all I'm going to say about that, all right?
You say you don't believe in dinosaurs and survived?
I did not say that. I just don't believe that the world is billions of years old. So, all right, that's all we're going to say about that. So, that's something that's going to come up a lot, is carbon dating. So we're going to use one here with that, okay? So, first off, we got one more definition here. It's a half-life. All right, what is a half-life? So a half-life is time required for half of a given substance to disintegrate. Can't spell. Disintegrate. And apparently I still didn't spell right. Thank God for, there we go. Thank God for spell check. It's the greatest creation known to man. All right. So, for this example here, I'm going to tell you that so carbon-14, the thing I was just talking about for radiocarbon dating. All right, it has a half-life equal to 5,715 years. I agree. All right, so it's a half-life of 5,715 years. Okay? So we want to find an exponential decay model and then use it. All right, so this is exactly what the scientists would use to try to date things by carbon dating. All right, so again, our standard form is A0 equals A sub 0 e to the kt. All right, so now we have this thing called a half-life. And why do they use half-life? Well, it's a lot easier, when you're talking about something that takes thousands of years. It's a lot easier to work with a number 5,700 versus 10,000, especially when you get to a certain point when you're talking millions or billions and that kind of stuff. All right, so that's why they use a half-life, and it's a lot more reliable. Okay, so for us though, that just means we want this to be over 2, right? So we want the life of it. So this A would be the value at a certain point. So we want to find out where the half-life is, because that's what we know. Okay, so we divide that by 2. So then we set that equal to this, A sub 0 of our e to the k. Now we know the time is 57:15. All right.
Like on the first problem,
Uh-huh.
why, since it was like a million or whatever, why did we just put 200 instead of?
We just used the numbers we had, and there's no sense in putting them in zeros as long as it was in the same units. You wouldn't have to, no. All right, so there we go. That's our model. So let's solve this guy. So I'm going to take this guy and really just divide by a sub 0. Now we just know that this thing here, if I would flip this up, it would be over 1, and I could cross out A and A, right? All right, yeah, they're not exactly the same, but it's an A and an A, even though one has a sub 0. So that side's just going to end up being 1/2. Okay, so we have 1/2 equals e to the 5715k. Okay, so then to get rid of that e, let's go natural log. So we have the natural log of 1/2 equal to 5715k. Divide both sides by 5715. And then I get k is equal to, really ugly, negative 0.000121. I think really, really tiny. All right. So then my decay model for this would be here. 0 or A equals A sub 0 e to the negative 0.000121 t. All right, so that's my model. All right. Oh, we have 5 minutes? Yeah, we're good. 6. Okay, we're good. All right, so there's my model for using the decay model for the carbon-14. You guys with me on how we got that? All right, so now let's use this guy. So we're going to say that this is actually a realistic problem. So 1947, the Dead Sea Scrolls. You guys know what the Dead Sea Scrolls are? What's Dead Sea Scrolls? Go ahead. Yeah. So they were found with 76% of their original carbon-14. They'll think we were messed up. Oh. It'll be all on video. Just, yeah, 100 years from now, someone's going to look back and go, oh my God, TikTok is a mess. All right, so now that we have this, we have our model, okay, and we know that there's 76% of the item remaining. All right, now we'll just change our percentage into a decimal. So it would be 0.76, right? And that would be 76% of our original value, right? Now, original value is our a sub 0, okay? And then that's equal to essentially original value, e to the negative 0.000121 t. That was just my model from above. All I did was just made this 76% of the original, all right, whatever that amount was. All right, so if I want to solve for t, I can just do this, and those are both gone. All right, so in theory, when you're doing this, you could really just skip to this step here. All right, in all honesty, but I wanted, at least for this one, I wanted to write it out. All right, so from there, I get this. Let's apply the natural log to both sides. Natural log, natural log. So now I'm going to end with natural log of 0.76 is equal to negative 0.000121 t. Divide both sides by negative 0.000121. 0.000121. I get sick of writing that number. All right. Punch that into a calculator. I get 2268 roughly. Again, I think this comes out to like 22,6,7,8,9,2 or something like that. Okay, so I'm just going to make it rounded up to the nearest year, 2268. Now, does that tell us how old it is? No. All right. That tells you how much time has passed. All right, and they found this in 1947, right? So in 1947, that's what, 73 years ago, right? That was 73 years ago, if we're going from based off of 2020. So then I would take this and add 2268 plus 73. That's going to be 2341. Okay, so right there, that would, according to that, that would be 2,341 years old, which would be what, about what, 320 BC. All right. Questions?